Hi, in this video we'll go over how to use AVR microcontrollers to make switch mode power supplies. We'll start by going over the fundamentals of switch mode regulation and compare these methods to linear voltage regulators. We'll then look at an implementation of a buck step-down converter using the core-independent peripherals of the AVR as the switching controller to eliminate the need for a dedicated controller IC. A switch mode power supply relies on periodic switching to generate voltage pulses, which is then smoothed out using theoretically lossless components like inductors, capacitors, and diodes. In an ideal case, switch mode power supplies have a 100% efficiency, but due to some resistance in the components and power used in feedback regulation, we typically see an efficiency of around 70 to 85%. However, it is achievable with efficiencies on the high side of 90% with proper component dimensioning, layout, and regulation circuitry. In contrast, more traditional linear power supplies rely on dissipating excess energy through heat using resistance. Efficiency in linear regulators is determined by the current and voltage drop through the regulator, and for most applications we typically see an efficiency of around 40 to 60%. For applications where linear regulators fall below this efficiency, we should consider using other regulation techniques, like switch mode regulation, to reduce wasted energy and heat. Another advantage in using switch mode regulators compared to linear regulators is that changing the circuit topology allows for the power supply to work either as a step-up or step-down converter. Certain topologies, like buck-boost converters, can even step the voltage in both directions. These advantages do, however, come at the price of a more complex system. A low dropout voltage regulator typically only needs an input and output capacitor with predefined values, while the components in a switch mode regulator needs to be dimensioned on a system-to-system basis. Let's focus on the buck step-down converter. The inductor and capacitor is set up as a low-pass filter to smooth out the voltage pulses generated by the switch, while the diode works as a one-way gate to allow current through the inductor even when the switch is open. This circuit will resist the rapid changes in voltage caused by the switch, which results in an output voltage equal to the input voltage times the duty cycle. The load works as a dampening resistor in an RLC filter and affects the step response. Changes in the load current will affect the time it takes for the capacitor to reach a certain voltage level. In practice, this means that using a constant duty cycle for the switch, the regulator will output different voltages for different loads. We can counter this effect by adding a feedback loop to the switch controller. The feedback loop will use some variation in either current, voltage, or both to adjust the duty cycle. This ensures that the capacitor always has enough time to reach the desired output voltage for any load. The switching control is often handled by a dedicated controller IC, as the regulation process is very active and would require too much monitoring by the CPU for it to handle any other tasks. The power consumption of a CPU is also much higher than the other solutions and would therefore reduce efficiency. However, using the core-independent peripherals of the AVR, we can make a switching controller using only a few peripherals, leaving the core and other peripherals free. This reduces the number of active components in the circuit, resulting in lower cost and complexity. Let's first replace the switch in our original buck topology with a transistor switching circuit. Using an NMOS transistor with a bootstrapping circuit, we can achieve high-side switching with low on resistance and reliably switch higher voltages than the logic level voltage of the microcontroller. There are multiple ways to implement the feedback loop, but in general, they all follow similar principles. Let's use closed-loop voltage-controlled feedback for simplicity. This can be implemented using an integrated op-amp, analog comparator, and a timer. The op-amp is set up as an error amplifier and will output the deviation between the actual and desired output voltage by referencing it to a voltage provided by the digital-to-analog converter. This deviation can be used as a reference to set the duty cycle of the switch for different loads. This is done by routing the output of the error amplifier to the negative input of the analog comparator and compare it to a triangle or sawtooth signal. The reference signal is generated using the waveform generation functionality on the timer counter B peripheral. The timer is set to 8-bit PWM mode with a 50% duty cycle and frequency equal to the desired switching frequency. As the timer can only output square waves, an external RC filter has to be added to shape the signal. To control the gain of the amplifier, as well as compensating for phase delay, we add an error amplifier compensation network consisting of a few resistors and capacitors. The dimensioning of this network should cancel out the phase effects of the LC filter on the output of the buck converter, as well as amplifying the DC error voltage correctly in relation to the amplitude of the voltage ripple. A simplified guide to choosing the hardware components can be found in the app note linked in the description. If you have an AVR without an op-amp, it is possible to make such a controller without it as well, as we can see here. Its characteristics might be slightly worse than the op-amp version, but it is still fully functional. The controller can be simplified even further if we remove the timer, using only the comparator to switch off the transistor when the voltage exceeds the threshold voltage. This solution, however, will not have a fixed switching frequency. This will have an effect in regards to efficiency and voltage ripple. Both of the solutions shown here are simpler in supporting components as well, making it easier to design and is more suited for multiple output voltages as there is no phase compensation. Looking at some of the measurements from the different implementations, we can see some of the expected differences. The choice of regulation technique will vary depending on the specific use case, though looking at both the hysteresis methods, they would typically need further regulation using an LDO. The efficiency of this power supply will be better than using an LDO by itself, as the voltage drop across it will be less than for the unregulated voltage supply. The controller should in theory not have any effect on the power rating of the system, but in practice, the minimum duty cycle of the controller as well as its sensitivity has a small effect. As the best standalone solution was the closed-loop voltage control regulator, further testing was done on this system. It was tested to an output power of up to 5 watts with the listed buck components. However, the layout of the components will affect the performance, so it is advised to step up the power gradually to make sure everything is working as it should. As efficiency is highly dependent on proper layout, this has to be measured on a system-to-system basis. Using the core-independent peripherals in this way can reduce cost by reducing the number of specialized ICs used in the circuit. Dedicated switch mode ICs can provide higher efficiencies and more safety features, but this is redundant in a lot of cases. It is also possible to include some of these safety features, like for example current limiting using additional peripherals if needed. These controllers also provide the possibility to adjust the output voltage purely in software by changing the reference voltage on the op-amp. This provides easier compensation for a more accurate target voltage, and adds flexibility for the same circuit to be used in different systems with different voltage requirements. The code for these switching controllers, as well as additional documentation, can be found through Atmel START. There's a link to an app note in the description which provides a better understanding of the buck implementation using the closed-loop voltage-controlled feedback. For more information about benefits and possibilities using the core-independent peripherals as a feedback controller for switch-mode power supplies, Microchip provide a development kit using the PIC16 series of microcontrollers. The documentation for this kit provides multiple implementations of switching controllers, as well as layout for the buck converter, making it easy to convert that design to the AVR. We hope that you've enjoyed this video and that the core-independent peripherals can help take your projects to the next level.